Welcome back to our series on mathematics and machine learning. Last time, we looked at a few different types of cost functions. But today, we're going to zoom in and clear up something that trips a lot of people up. The difference between a loss function and a cost function. Let's get right to it.
So, loss function, cost function. Are they the same thing? I mean, you'll hear people use these terms interchangeably all the time, and you can kind of get away with it. But if you're actually training a model, you've got to know the difference. It's absolutely critical because they measure error at two totally different levels. Getting this right is really the key to understanding how a machine actually learns.
You know, it all boils down to a pretty simple idea. Before we can tell a model, hey, get better, we first need a really solid mathematical way to tell it exactly how wrong it is right now. And that's where these two functions come into play. All right, let's start at the smallest possible scale. We're talking about a single individual mistake. This is the world of the loss function.
So picture your giant data set, right? Thousands, maybe millions of data points. The loss function, it doesn't care about all of them at once. Nope. Its job is to look at just one of those data points, just one image, one row of data, and figure out the error for that single prediction.
And here's the perfect way to think about it. If your training data is like a giant test with thousands of questions, the loss is just the penalty you get from messing up, say, question number 57. It's that specific, isolated score for just one instance.
So how do we actually calculate it? Well, a super common way, especially for regression problems, is called the squared error. It's simple. You take what the model predicted, you subtract the actual right answer, and then you square that result. That gives you a nice positive number that tells you the size of the error for that one point.
Okay, so if loss is about just one mistake, how do we grade the whole performance? Well, for that, we need to zoom out, and now we can talk about the cost function.
The cost function's job is to take all of those little individual penalties, the loss from every single example in your training set, and roll them all up into one single meaningful number. It gives us the big picture.
And this just brings the analogy home perfectly. The loss function tells us we got question 57 wrong. The cost function takes the results from all the questions, does some math, and tells us we got an 85% on the entire exam. See? It's the overall performance metric.
And mathematically, it's often as straightforward as it sounds. We calculate the individual loss for every single data point, we add them all up, and then we just take the average. This average is our cost. You'll often hear it called the mean squared error, or MSE.
Okay. So one is for a single point, the other is for the whole data set. Big deal, right? Well, yeah, it's a huge deal. Why is this distinction so incredibly important for actually training a model? This is where it all clicks. This table right here, this really nails down the different jobs these two functions have. Let's walk through it. First, look at scope. We've got that down. Loss is for one example, cost is for the entire data set. Easy enough. But now, here's the crucial shift. Look under input. The loss function, it uses a prediction and a correct label. But the cost function, we start to see it as a function of the model's parameters. And that changes everything. It means its purpose isn't just to measure a penalty anymore. Its purpose is to define the entire goal for optimization. The cost becomes the one number we are trying to shrink by changing the model itself.
So this is the big mental shift we have to make. We start by calculating error based on the data. That's the loss. But then we reframe the total error, the cost, as a problem related to the model's internal settings, its weights and biases. And why do we do that? Because we can't change the data, but we can change the parameters. That's the whole point of training.
So this slide lays out the entire game plan. Step 1, we calculate the loss for every single point. Step 2, we average them all together to get the cost. Step 3, we start thinking of that cost number as being controlled by the model's internal knobs and dials. And finally, step 4, the entire goal of training becomes finding the exact combination of those knobs and dials that makes that final cost number as low as it can possibly go.
This goal, this mission to minimize the cost, leads to a really powerful way to visualize what's happening. Let's picture this as a kind of landscape.
I want you to imagine that every possible combination of your model's parameters maps to a single point on a vast surface. The height of the surface at that point, that's the value of your cost function. So high altitudes mean lots of error, low, deep valleys mean very little error. Our training algorithm, something like gradient descent, It's basically like a hiker dropped onto this landscape, and its only job is to walk downhill until it finds the absolute lowest point in the entire terrain.
And that's the whole objective, to find that one single point, that one optimal set of parameters that sits at the very bottom of the deepest valley. That's it. That is our trained model.
But this brings up a really fascinating question. Are all of these landscapes the same? I mean, what if a landscape is full of little potholes and traps and hills, making it super hard for our hiker to find the true bottom? What actually makes a cost function good for optimization?
Well, it turns out the shape of that landscape is everything. And the ideal shape, the perfect, easy-to-navigate landscape, has a special name, a convex function. That is our topic for the very next explainer, where we're going to see why having a simple, bowl-shaped landscape is pretty much the holy grail for machine learning optimization. I'll see you there.